There's two topics I'm going to cover in this video. It's sequences being monotonic and bounded. And what we're going to have to find out is you're going to be able to work with a sequence and figure out if it is monotonic or not, and if it is bounded or not. So let's first talk about monotonic. You're probably familiar with the word monotone. If you know who Ben Stein is, he's made lots of money off being monotone. He's the Clear Eyes commercial guy. Clear eyes gives you the power to moisturize. Wow, yeah, that guy. He's on Ferris Bueller and Richie Rich and lots of other movies. But anyway, so monotone has the idea of just being one thing all the time, one tone. Mono means one, tone, monotone. In math, what monotone means is that a sequence is either strictly non-increasing or strictly non-decreasing. Now I know this might be a little confusing that we use these terms instead of just saying increasing and decreasing, but there's a specific reason we don't. We're allowing for the sequence to stay constant. Okay, so what non-increasing really means is that we are either decreasing or staying constant. And what non-decreasing means is that we are either increasing or staying constant. It can be either one. So being constant will work for either scenario. But non-increasing means you're not increasing, you're either decreasing or staying the same. So non-increasing would look like this. And so on. So the next term is always smaller than the one that came before it, or the one that comes before is always bigger than the one that comes after, if you want to look at it that way. But that's what non-increasing would look like. And non-decreasing would just be the opposite. Be A1 is less than or equal to A2 is less than or equal to A3 is less than or equal to A4. So it's either growing or staying the same all along the way. Okay? To determine if a sequence is monotonic, you basically want to look at the first 3 or 4 terms, and then you're going to have to test it using an inequality. So let's look at some examples. But that's what needs to be done. You look at the first 3 or 4 terms, and then you test it using an inequality. So for example, an equals 2n over 1 plus n. So I'm going to pull up the calculator, and I'm going to plug this equation, 2x over 1 plus x, into the calculator, and then go to the table. I'm just going to plug in 1, 2, 3, 4, 5 so I can just see what the first 5 terms look like. Okay, now, this does appear to be monotonic from the first 5 terms. I can't guarantee it just based on the first 5 terms, but from all appearances right now, it is monotonic. It just goes up. It just increases. It goes 1, 1.3, 1.5, 1.6, 1.66, and so on. So my first test checks out. It appears to be monotonic, and in fact, it appears to be non-decreasing. Non-decreasing. So if I do that, non-decreasing, here's how you test it with the inequality. You take your original function. Since it's non-decreasing, if you look back up here, non-decreasing, just make sure you know this one goes with this one, this goes with this. Non-decreasing is less than or equal to. So I'm going to do this is less than or equal to, and then I'm going to rewrite the original again, but I'm going to replace all of the n's with n plus 1. Okay, now if I simplify that, I'm just simplifying the right side. I get 2n plus 2 over n plus 2. Okay, so now I'm going to cross multiply. So I'm just going to replace this with its new form here. All I did was simplify, and then I'm going to cross multiply. So I get 2n times n plus 2 is less than or equal to 2n plus 2 times 1 plus n. And over here on the right I'm going to distribute, so I get 2n squared plus 2n less than or equal to, and if you FOIL all this, you should get 2n squared. Oh, I'm sorry, I need to back up. This was 4n right here, 2n squared plus 4n. And then if you FOIL all this out, you should get 2n squared plus 4n plus 2. So you only need to take this as far as you need to see if it's true or not. Because what I should technically write here is a question mark above these. We're not stating this is true, we're testing to see if it's true. And this one is. Clearly, if you take 2n squared plus 4n and then you add 2, it's going to be bigger than if you don't. So this does check out, which means that we have determined this is in fact monotonic. It is confirmed to be monotonic. And we did that again by testing the first 5 terms, just looking at them in the calculator, and then setting up this inequality where we start with the original, and then we make an inequality where we compare it to what the n plus 1 term would be. So we just changed all the n's to n plus 1. Okay, another example. 3 plus negative 1 to the n. So let's plug this in the calculator. 3 plus negative 1 to the n. And we go to the table. And hopefully you can tell right away this is not monotonic. We don't even have to bother doing the test because this is clearly not monotonic. It goes from 2 up to 4 and then back down to 2. So we can either increase or decrease, but we can't do both. And it's clearly doing both. It's increasing to 4, decreasing to 2. Increasing to 4, decreasing to 2. So this, right away we can tell it's not monotonic. Okay, let's try 1 or 2 more examples with this before we look on unbounded. We have an equals n squared over 2 to the n minus 1. So again, first step when you're testing if something's monotonic or not is to plug it in the calculator, or you can do this by hand and test the first 4 or 5 terms. So x squared over 2 to the x minus 1. Okay, so again, if you look carefully at this, you should be able to tell right away this is not monotonic. It starts at 1 and then goes up to 1.33, but then down to 1.28 and down to 1.06. So even though it may decrease from there on out, the fact that it started by increasing and then decreased says it's not monotonic. It ruins it right away. So this one is also not monotonic. One last example. 3 minus 1 over n. So let's start by just looking at the first few. 3 minus 1 over n. We go to the table. And initially, it does appear that it's going to work. It appears to be non-decreasing because it's always increasing, so that means non-decreasing. So we can do this, test this to see if it's true for every point by doing the inequality. So we'll do 3 minus 1 over n is less than or equal to, so I want to be very clear here. Since we were non-decreasing, that's why I do less than or equal to. If we were non-increasing, then I would do greater than or equal to. So we get 3 minus 1 over n is less than or equal to 3 minus 1 over n plus 1. So just want to make sure you understand how to set up this inequality. On the left side, no matter whether you're increasing or decreasing, on the left side you always start with the original, in this case 3 minus 1 over n. On the right side, you just replace all the n's with n plus 1. And then from there, you solve, and you determine if this is true. Because we're not stating it is true, we're trying to determine if it's true. So I subtract 3 from both sides, and I get negative 1 over n is less than or equal to negative 1 over n plus 1. Okay, I don't really like having the negatives, so let's multiply both sides by negative 1. But when you do that, remember, you have to flip your inequality. Okay, then cross multiply. When you cross multiply, the top spot always keeps its spot. So 1 times n plus 1 comes over here. 1 times n comes over here. And clearly that is true. N plus 1 is greater than or equal to n. So this is monotonic. Okay, now let's move on to bounded. Bounded sequences. Before we say anything else about bounded sequences, I want to make sure you understand the ideas of monotonic and bounded are completely independent of each other. You can be one but not the other. You can be both. You can be neither. So these are not related in any particular way. These are two separate ideas. They often ask them in the same question, but they're not related. It's not that if you're bounded you're going to be monotonic or vice versa. You can be any combination of these things. So a sequence is bounded if it has a value it never goes above and a value it never goes below. Another way to say this is it always has a ceiling and it always has a floor. There's some maximum. It's fine if it equals that maximum, but it has to have a spot that it never goes above. It also has to have something it never goes below. And basically to determine this, you want to test the first few terms and the limit as n goes to infinity. If you look at those two things, it should be very clear whether you are bounded or not. So we're just going to look at 3 examples, and then we'll call it a day. So, first, 3 plus negative 1 to the n. Okay, if we look at the first 4 terms, it actually works out perfect in your calculator. If you just look at the first 4, then you can plug in 10, 100, 1000. Well, we'll do 10,000, that's fine. Okay, if you look, the question you need to ask yourself is, does it appear that there's a number it never goes above? Well, yes, it appears it never goes any higher than 4. And does it appear that there's a number it never goes below? Yes, it appears it never goes lower than 2. So it really doesn't even matter what the max and the min are. You don't have to tell me what they are. You just have to see that there is one. And since there is a max and there is a min, that means it's bounded above and below. So it is bounded for this first example. So that first example is bounded. Never goes above 4, never goes below 2. So it's bounded on both sides. So we call it a bounded sequence. Okay, let's try this next one. 2x over parentheses 1 plus x. Go to the table, and we'll see the first few terms. Alright, based on this, you have to ask, is there a number it appears it never goes above? And to me it would appear that it never goes above 2. It seems to get really close to 2 as we're going to infinity, but it's clearly just approaching 2 and it's not growing and growing. So it appears to have a maximum or a ceiling of at 2, and it also appears to never go below 1. So this is bounded because it's bounded above by 2 and bounded below by 1. Because remember, sequences don't exist in the negatives. We never will plug in negative numbers. So it doesn't matter what happens before 1 because we don't start until 1. So it is clearly bounded below by 1 and above by 2. Final example. We'll do 2 raised to the x minus 1 divided by x squared. The process, one more time, for looking at bounded sequence to determine whether a sequence is bounded or not is looking at the first few terms and then also looking at the limit as you go to infinity. Okay, so if you look at the first few terms and the limit as it goes to infinity, it appears it never goes lower than that 0.75 number. Everything else appears higher. So it does look like it has a floor. It never goes below 0.75. But as you go out to infinity, you can tell the number is just getting bigger and bigger. So if you look here at 10, we're at 10. And then at 100, we're at 1.3 times 10 to the 26th. So I don't even know what number that is. That's way beyond billion and trillion and all that. So it's huge. It's 1.3 followed by like 25 zeros. Huge. And then it's so big the calculator can't even calculate it at 10,000. So it's clearly growing without bounds. So it has no maximum. It just goes up to infinity, so it's not bounded because it does not have a spot it never goes above. It goes up to infinity, so it is unbounded or not bounded. So the bottom line is, you want to see, is this thing going to infinity or negative infinity? If it is, then you're unbounded. Because it doesn't have a max or it doesn't have a min, one or the other. If it appears to just approach a number, then it is bounded. So if it has a max and it has a min, something that never goes above and below, it's bounded. If it doesn't have one of those, if it doesn't have either of those, it's unbounded.